Welcome to SAM Networking Labs. Today we are going to work through practical, dynamic routing with RIP version 2. This is a foundational lab that will teach you how to build a multi-router topology, configure interfaces, enable dynamic routing, and verify end-to-end communication. This practical follows the exact workflow that network engineers use in production environments: build the topology, cable the devices, configure interfaces, verify local connectivity, enable the routing protocol, verify learned routes, and test end-to-end communication. Take your time with each step and make sure you understand the concepts, because dynamic routing is a core topic in networking exams like TNSA and CASNB. Let us begin by understanding the objective of this lab. By the end of this practical, you should be able to build a 4-router topology, configure router interfaces, verify connectivity, configure RIP version 2, verify learned routes, and test end-to-end communication. This lab uses 4 Cisco 2911 routers. We are using the 2911 model because it provides multiple gigabit Ethernet interfaces, which makes it ideal for routing labs in Packet Tracer. You will also need 3 copper crossover cables to connect the routers. The first step is to build the topology. Open Cisco Packet Tracer and place 4 Cisco 2911 routers on the workspace. Arrange them in the following layout. Imagine R2 in the center. R1 connects to R2 on the left. R3 connects to R2 from the top. R4 connects to R2 from the right. This creates a hub and spoke topology with R2 as the central router. Once you have placed the routers, rename them to R1, R2, R3, and R4. You can do this by clicking on each router and changing the display name. Now we will connect the routers using copper crossover cables. The connections are as follows. Connect R1 G0/0 to R2 G0/0. Connect R2 G0/1 to R3 G0/0. Connect R2 G0/2 to R4 G0/0. Make sure you are using copper crossover cables and not straight through cables, because we are connecting routers directly to routers. Router-to-router connections require a crossover cable. The topology should now look like R2 in the center with R1 on its left connected through G0/0, R3 on the top connected through G0/1, and R4 on the right connected through G0/2. Next we need to assign IP addresses to each interface. Let us look at the addressing scheme. R1 G0/0 will be 192.168.12.1 with a subnet mask of 255.255.255.252. This is a 30-bit mask which gives us 2 usable host addresses, perfect for point-to-point links between routers. R2 G0/0 will be 192.168.12.2 with the same mask. R2 G0/1 will be 192.168.23.1 with a 30-bit mask. R3 G0/0 will be 192.168.23.2. R2 G0/2 will be 192.168.24.1. And R4 G0/0 will be 192.168.24.2. Notice the pattern. The first 2 octets identify the link. The third octet identifies the pair of routers. The fourth octet identifies the specific router on that link. Now we will configure the interfaces on every router. Enter privileged exec mode with the enable command. Enter global configuration mode with configure terminal. Select the interface using interface G0/0 or interface G0/1 or interface G0/2 depending on which router you are configuring. Assign the IP address and subnet mask using IP address followed by the IP and the mask. Bring the interface up with no shutdown. Exit back to global configuration mode. Repeat this for each interface using the IP addressing table we just reviewed. On R1 you only configure G0/0 because it only has one connection. On R2 you configure G0/0, G0/1, and G0/2. On R3 you configure G0/0. On R4 you configure G0/0. After configuring all interfaces, it is time to verify interface status. On every router, use the command show IP interface brief. This command displays all interfaces, their IP addresses, and their status. You should see interface status as up and protocol as up for each configured interface. If an interface shows administratively down, it means you forgot the no shutdown command. Go back to that interface and issue no shutdown. If it shows down or down, check the cable connection and ensure it is plugged into the correct interface on both ends. Also verify that you are using a crossover cable for router-to-router connections. Now we test direct connectivity. Ping only directly connected neighbors from each router. From R1, ping 192.168.12.2 which is R2G0/0. From R2, ping 192.168.12.1 which is R1G0/0. Also from R2, ping 192.168.23.2 which is R3G0/0. And ping 192.168.24.2 which is R4G0/0. From R3, ping 192.168.23.1 which is R2G0/1. From R4, ping 192.168.24.1 which is R2G0/2. All these pings should succeed. If any ping fails, check your IP addressing and interface configurations again. Next we examine the routing table on each router. Use the command show IP route. This command displays all routes that the router knows about. At this point, each router only knows about its directly connected networks. For example, R1 will only show network 192.168.12.0. R2 will show 192.168.12.0, 192.168.23.0, and 192.168.24.0. R3 will only show 192.168.23.0. R4 will only show 192.168.24.0. There are no RIP routes yet because we have not configured RIP. Notice that R1 does not know how to reach 192.168.23.0 or 192.168.24.0. R3 does not know how to reach 192.168.12.0 or 192.168.24.0. R4 does not know how to reach 192.168.12.0 or 192.168.23.0. This is why we need dynamic routing. Now we configure RIP version 2 on all 4 routers. On R1, enter global configuration mode and use the command router RIP. This enters RIP configuration mode. Then use the command version 2 to set RIP to version 2. Version 2 supports classless routing and includes subnet mask information in its updates, which is important for our network. Then use the command no auto summary. This prevents RIP from automatically summarizing routes to classful boundaries, which is necessary when we have discontiguous networks or networks that do not fall on classful boundaries. Then use the command network 192.168.12.0. This tells RIP which interfaces to advertise. On R2, you enter router RIP, then version 2, then no auto summary, then network 192.168.12.0, network 192.168.23.0, and network 192.168.24.0. This advertises all 3 networks that R2 is connected to. On R3, you enter router RIP, version 2, no auto summary, and network 192.168.23.0. On R4, you enter router RIP, version 2, no auto summary, and network 192.168.24.0. It is important to understand that the network command must match the classful network address of the interface you want to advertise. For example, 192.168.12.0 is the network address for the link between R1 and R2. Even though the interfaces use a 30-bit mask, the network command uses the classful network address. After configuring RIP on all routers, wait a few seconds for the routing protocol to converge. Then verify RIP configuration using the command show IP protocols. This command displays information about the routing protocols running on the router. You should see that RIP is running, it is version 2, auto summary is disabled, and you should see the networks that are being advertised. You should also see the neighbors that RIP is exchanging updates with. Now verify the routing table again using show IP route. This time, you should see routes that begin with the letter R. The R stands for RIP. These are routes that were learned through RIP. For example, on R1, you should see an R route for 192.168.23.0 and an R route for 192.168.24.0. On R3, you should see R routes for 192.168.12.0 and 192.168.24.0. On R4, you should see R routes for 192.168.12.0 and 192.168.23.0. You will also see the next hop address and the administrative distance and metric for each route. RIP uses administrative distance 120 and metric is hop count. Finally, test remote connectivity. Ping routers that are not directly connected. From R1, ping 192.168.23.2 which is R3G0/0. Also from R1, ping 192.168.24.2 which is R4G0/0. From R3, ping 192.168.12.1 which is R1G0/0. From R4, ping 192.168.23.2 which is R3G0/0. These pings should now succeed because RIP has exchanged routing information and each router knows how to reach every other network in the topology. If any ping fails, check your RIP configuration and ensure that all networks are advertised correctly. The final step is to save the configuration on each router. Use the command copy running config startup config. This saves your running configuration to NVRAM so that it persists after a reload. This is a good habit to develop because it prevents loss of work if the router reboots. Let us review the learning summary for this lab. By completing this practical, you have learned to select and place routers in a topology. You have learned to connect routers using the correct cable type, which for router-to-router connections is copper crossover. You have learned to assign IP addresses to router interfaces using a 30-bit mask for point-to-point links. You have learned to verify interface connectivity using show IP interface brief. You have learned to test local connectivity by pinging directly connected neighbors. You have learned to enable dynamic routing by configuring RIP version 2. You have learned to advertise networks using the network command. You have learned to verify learned routes using show IP route. You have learned to confirm RIP operation with show IP protocols. And you have learned to test end-to-end communication using ping. This sequence follows the same workflow used by network engineers: build, cable, configure, verify interfaces, verify local connectivity, enable routing, verify routing, and test end-to-end communication. This is a repeatable pattern that you will use in many networking labs. Thank you for joining me today at SAM Networking Labs. Practice these steps in your packet tracer environment. Create the topology, configure the interfaces, enable RIP, and test connectivity. The more you practice, the more comfortable you will become with dynamic routing concepts. These skills are essential for any network administrator and will appear on your exams. Good luck with your studies and we will see you in the next lab.